Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage. Well, here we've got a problem that involves a organic chemistry reaction. We've got this C2, so we know it's got an ethyl group, and then we've got bromine attached to it. A hydroxide reacts with it, and we make, in this case, an alcohol, ethanol, and we have some bromide ions left over. Let's just quickly go to this. In organic chemistry, you'd have to explain how this happens. Well, this hydroxide is attracted to this carbon. There's a slight positive charge here. And this electron here goes to the bromine. So we need a collision between the hydroxide and this carbon in the ethyl arrangement. And we produce this weird thing, which is wrong because we've got 5 almost bonds to our ethyl group, and we know our carbon, so we only have, notice you have 4. This has got a negative charge. 1 too many electrons. Well, the bromide escapes, and we're left with our alcohol, in this case with the OH there, and bromide ions floating around. And they refer to this as a nucleophilic substitution. They even have a abbreviation for an SN, and then this 2. But you'll get that in organic chemistry, and you know a little bit about it already in terms of carbon bonds and their structures. Also, notice this involves a collision of this bromomethane. It's going to have a certain concentration and a collision of this hydroxide. So both of these have got to collide and to make this thing. So we've got a collision of these two. So the concentrations of these two might be pretty important. But let's get back to our problem, because they're telling us in this reaction they've done it a number of times at different concentrations. Here's at various concentrations where they adjust and change the concentration of the bromomethane and also the hydroxide ion, and then they've come up with a speed as to how fast the reaction is going. Here we see the products are being made, but this speed is how quickly the concentrations of these change. And of course, with any rate or speed, we've got a concentration unit, which could be pressure. In this case, it's molar. And of course, we have to have time per second. If it's a speed, it's got to be per time unit. And each one of these has a per time unit. In this type of problem, they'll want you to find out the rate law expression, where we try and find out how quickly the reaction is going. And it's based on a constant and the concentration of our two reactants. We're going to ignore the products. That's one of the nice things about this unit. We wouldn't have to worry about the products because only the reactants are going to be things that we worry about. We think that they may be involved because they are reactants, but we'll find out how involved they are by putting an exponent here, and that's what we have to find, the exponent. And one of the nice things about these rate laws is these exponents will typically be a whole number, 0, 1, or 2. In a weird case, they could be a -1. You could even have a 1.5, but in AP chemistry, you're not going to worry about that. So if you wanted to guess right now, you could say 0, 0, or 1, 1, or 0, 1, but let's not guess. Let's find out how to find the answer. Well, the first thing you should do is we're going to look at how these concentrations work with the rate. And we want to compare the rates and compare the concentrations. Now notice we have different exponents here, 10 to the -4, 10 to the -3, which is going to make comparisons a bit difficult. We should change all these values, these rate values, so that we can compare them. Make them all 10 to the -4. Now, if you're really good with numbers, you may not have to do that, but for a comparison, I very, very strongly advise that you change these into the same power of 10. So that's easy to compare 7.41 to 14.8. We can see that this is about a double, which is harder to see when you've got a different scientific notation exponent. And of course, you're good at moving decimal places, 1.11 to 10 to the -3. And we'll see that this reaction is a little bit slower than our previous one. Not a simple ratio, it looks like. And we'll do this one too. We've got our numbers here. They're easy to compare. We can say this is our fastest reaction, second fastest, and compare these values. We can then ignore the 10 to the -4 for comparisons, because that's what we're going to do. We're going to do some comparisons, and with those comparisons, we're going to figure out what these whole number exponents are going to be. That tell us how important these things are in the rate of the reaction. So our first question here that I've set up, we've got our reaction. How did the concentrations of the reactants change between trial 1 and 2? So I'm looking at 1 and 2, and I see that the bromoethane is doubled. That's what you want to see. Yeah, this is a doubling, twice as concentrated. Now, the hydroxide isn't changed. That's what we want. We want a situation where we're only changing one item, so we can see the effect of the bromoethane because the hydroxide hasn't changed any. Now look, doubling the bromoethane, here's our rate, 7.4, 14.8, about double. So if we double the bromoethane, we double the rate. That tells us how important the bromoethane is. In fact, in this case, if the same thing happens, in other words, we have a doubling and a doubling, that means that this is important to the first power. If we double this, this becomes twice as great, our rate becomes twice as great. Now, if this had been a 0, there would have been no change made to our rate because bromoethane to the 0 power would be 1, and any change in its concentration would not affect our rate, but that didn't happen. We see in this experiment that this 1 is what is the power of our concentration of bromoethane. This is its value. It is good to the first power. And we've already got now half of our answer. This makes sense, 1. Now, let's figure out what's going to happen with the hydroxide. Well, we couldn't use trial 1 and 2 with the hydroxide because it didn't change. So that's not going to be useful. And of course, we were changing the bromo here. Now, here again, we're changing the concentration of the bromoethane, and it's sort of an unusual change, but not the hydroxide, so that's not going to be useful. But here, I'm looking at a 0.52, and I see a 0.52 here. That means our bromoethane is not changing, but our hydroxide is. And that's why we're going to be looking at our next situation where we compare trials 2 and 4. Now, I've got our table duplicated here because in trial 2 and 4, the bromoethane isn't changed. That's good. We don't want to have complications with bromoethane. We want to see what's happening to this hydroxide. And here I see the hydroxide 0.15 and then 0.45. So there's no change in the bromoethane, but the hydroxide is tripled. So we made the hydroxide 3 times as concentrated. What happened to the rate of the reaction? Well, here I see it's about 15, and here my rate now is 45. It's tripled too. So we know the hydroxide's important, and tripling triples. So therefore, the hydroxide that we have here is also going to be important to the first power. If we triple the hydroxide, we would triple the rate. So we would know this is first order with respect to the bromoethane and first order with respect to the hydroxide. The overall reaction with both of these involved is a second order reaction, but with respect to bromo first, with respect to hydroxide first. Now, our next thing is to realize that we have ourselves a rate law expression, and we can end up using it. We've got the law, and we've got those exponents. And let's go back to this. The rate, how quickly a reaction goes, we're interested in that, dependent upon this concentration and this concentration. Well, what about this K? Well, this K is a constant. This multiplies times these two to give us our rate, and it's not going to change if the temperature doesn't change. Constants are beautiful. We love them. So right now, we can calculate this constant because we have data in a table. In fact, actually what we can do is we can take a trial. In fact, we'll take trial 1. You could have taken any one of these trials because this works for all of our concentration changes, and we can put our data in because we have how fast the reaction goes, 7.41 times 10 to the negative 4 molar, 0.007. Not very fast. Per second, it's a speed, molar per second, is equal to our constant that we don't know yet, but we do know the concentration of the bromoethane and the hydroxide. They're just given here. We've got all these values except for K. Now we can solve for K. I hope your algebra is good enough for this. We can therefore do this calculation. And that's where we pull up our calculator. We're going to solve for K. So I'm going to take my 7.41 and with our calculator times 10 to the negative 4, small number, divided by my 0.26, divided by 0.26, divided by 0.15. Now I'm doing a calculation. If this was an FRQ, I would double check my numbers. It's a pity to do all this work and get the wrong answer because you put down 7.14 instead of 41. And that, indeed, 7.41, e negative 4, divided by 0.26, divided by 0.15. Remember, you divide by everything in the denominator, or you could have multiplied these two and used a parentheses, but this is simpler. So let's see what our constant is. Enter. 0.019, that sort of makes sense. We have a small number divided by a number less than 1. Less than 1, we'd expect a larger number, 0.019. And that's good. Here it is, 0.019. Now, on a AP question, you're given a point for either the setup or the correct answer. But also they expect the unit. In fact, very often you can get the number wrong, and if you got the unit right, you get the second point because it's worth 2 points. The unit is critical in rate law expressions. And we know the rate always has to be in concentration per second. Like I said, this could be pascals or atmospheres, but usually it's molar. Now, if we divide this molar by this molar, we're left with, as a denominator, molar and per second. So this unit that is our K is going to be per molar per second. If we take this per molar per second and multiply it by molar and molar, we get our final unit, molars per second. Your algebra should be good enough for that. So this is our constant. And let me get my calculator because the constant is important. I'm going to store this quickly as X. That's my constant because I have a hunch that this probably is going to be used again. So let's continue with the problem. We've found the rate constant for this problem, and we know the order of the reaction. So any set of concentrations that we put in here at this temperature, we can find how quickly the reaction is going. This is just an amazing law, the rate law expression. Go back to my calculator here. Let's see what our rate would be for trial 3. Remember, we know our constant. If we took our constant, X, times the concentration at trial 3, 0.39, times, and trial 3, 0.15. If our rate law expression is right, and if our constant is right, we should get 1.1 times 10 to the negative 3. Let's see if we get that. There it is, 1.1. This rate law works, and we were able to prove it in trial 3. We didn't even need trial 3. We could have predicted what could have happened. All right, let's do the last part of this problem. Here it is. In the last part of this problem, they want to know how fast this reaction occurs for trial 5. They do the experiment again, and they say, here's our 2 new concentrations. Concentrations we haven't used before. What is the rate going to be? Now I'm going to look quickly, and I'm going to see that these 2 concentrations, 0.51 and 0.51, are pretty much greater than our typical concentrations we have here. So we'd expect a faster rate. But let's see what happens. Let's use our calculator and predict what the rate will be. Now we know our constant, X, it's good that I saved it, times this concentration, 0.51. Now, if this had been second order, we would have squared this. But this is first order. If this had been 0 order, we would have just ignored it, raised it to the 0 power. And then we know this is important too, so we're going to multiply our other 0.051. If I was clever, I would have just squared this, and we'd find out how fast this reaction goes. 0.0049, and I'm going to look here quickly. That's faster than these others, and we'd expect that. With higher concentrations, we expect faster reaction rates. So we now know how to deal with the rate law expression.